Hi, my name is Gracie. Welcome to my lab presentation for my second lab. So, for part one of the introduction, the purpose of this lab is to observe the laws of physics in real time, as similar to the last one. And this time we're attempting to quantify the gravitational force of an object as it falls from rest. The major models used in this lab is still Newton's second law, also known as the momentum principle, and this time we're factoring in the gravitational constant, or the force on an object due to gravity, as well as drag. Some experimental elements are the system being a small plastic coffee lid, and the surroundings being gravity, drag. And the initial conditions are that the coffee lid is being held at rest in the air. And the main objective is to compare the elements of movement observed versus the elements of movement when we plug in the same initial elements into a computational model, including and excluding drag. So a brief overview of the results is that compared to the plotted position versus time graph of the observed model, the computational model that included drag was closer to the graph taken from the observed model. And this is the video used. It's just my friend dropping a small plastic lid that's light enough to catch some drag. And the movement of this object falling was captured frame by frame using tracker, and we plugged in other physical elements such as length and mass to calibrate the whole thing. And we used the point mass feature to track the movement frame by frame. And in the computational model, we used the layout that was given to us by our professor, and we just plugged in some different elements such as the mass, the initial position vector, delta t, and here you can see B. This is the drag, and we did one where B equals 0, and then one where we calculated the drag, which I'll get to later. Right here. So the drag calculation, I did it in two different ways. And the first one, the instructions were that it was the opposite to the direction and the square of the object's speed. And I tried to do this with velocity, and it gave me a drag value that really threw off the computational model. So I tried to do the same thing with FNet, and I got this result, and it gave me much better results in the computational model. And here are some other calculations, such as the velocity we plugged in, FNet, the initial and final position, etc. And going back to the results, I was not able to put the observed position versus time and the calculated position versus time on the same graph because the amount of instances of delta t, like the times, were very different, as the initial video was only 1 second and it was done frame by frame, and this computationally was taken every 0.001 seconds, so we had a lot more iterations. And as you can see, with the drag model, the final position was a lot closer to the actual observed final position when we modeled it without drag. Without drag, it tended to overshoot the actual position in the y element, whereas with drag included, it was a lot closer to the observed. So possible sources of differences was that the computational model did not take into account the slight change in the x component that was observed, which is just because it's impossible to really drop something at a perfectly vertical angle and also calculate it using tracker at a perfectly vertical angle when it's done manually, as you can see here. And possible sources of error, as I mentioned earlier, was that I had a hard time putting the two graphs on the same graph in Excel, and that the code was given to us by the professor. I did not create it, so I was definitely not an expert in it. So in answer to the what does it mean question, I said the model with drag would predict terminal velocity if the video was longer. Since it wasn't very long, we didn't quite reach the point of terminal velocity where the drag equaled the force of gravity, which would create a net force of 0. In answer to the what if question, No, the final terminal velocity would not change if the velocity, mass, and speed were the same as they were in the original computational model if the object just hit the ground first. Thank you.